top, which is replication. And evolution can't begin until you've got some kind of, however crude, replication machine. Otherwise, information is not encoded into the future. So just to make that a bit simpler, we've got these three kinds of polymer and these various transactions. And if all three of those types of molecules had to come together before evolution could even start, I can't imagine how that would happen. So a number of years ago, many years ago now, people like Gilbert and Woese, and going back further, Crick and so on, proposed, let's simplify the whole thing down to one polymer. Let's just assume, throw away the DNA. That part's easy because there's not much difference between DNA and RNA, but also throw away the protein. So all we're left with now is RNA. RNA encodes the information. That's the part we're familiar with, but it would also have to do the catalysis. So that's the question. So you would need RNA to act as an enzyme, a ribo enzyme, we call them ribozymes. So ribozymes are enzymes, but they're not made of proteins, they're made of RNA. And one could then imagine putting this inside some sort of bag of phospholipids, having a metabolism, but an RNA catalyzed metabolism. Maybe we call this a ribozyme. Okay, now what would we need to make such a scenario plausible? RNA would have to do quite a lot of chemistry. Now, of course, this whole idea was greatly aided by this discovery of ribozymes by Czech and Altman and others back in the 1980s. But those ribozymes carry out a rather limited range of chemistry. Just the top line there, which is phosphoryltransfer. One exception to that, peptidyl transferase, but most do phosphoryltransfer. An RNA world, on the other hand, would have needed lots of metabolic ribozymes, doing much wider range of chemistry, including relatively difficult reactions like making carbon-carbon bonds, carbon-nitrogen bonds, whatever. So we can ask, what is RNA capable of? Well, let me start by saying what do we know for sure? So the ribozymes that we know about carry out phosphoryltransfer reactions for the main. So they're operating on a PO bond. So they're carrying out either hydrolysis or transesterification reaction, depending on what R1 is up at the top. So that's the range of chemistry. Now, how do they do it? There's actually two ways that RNA can do this, and it uses the same two ways that proteins do the same reactions. So on the left, you can use metal ions. So you use metal ions to activate nucleophiles, stabilize transition states, and so on. And most nucleases, like restriction enzymes, for example, polymerases as well, they use this kind of mechanism. But the group 1, the group 2, self-splicing introns, these larger ribozymes, that's basically how they work. On the other hand, the other way of doing it is to use general acid-base catalysis, where you use a general base to activate the nucleophile, the general acid to make a better leaving group. And enzymes like ribonuclease A do that, but the small nucleolytic ribozymes carry out these general acid-base catalyzed reactions. And here's an example. So this is one such ribozyme, the twister ribozyme. We solved the crystal structure of this a number of years ago now. And sorry, I don't have a pointer. I find this very, very unusual not to be able to point at things. But anyway, you see on the right-hand side, you've got a general base, which is removing the, I don't think there is one. Is it? Where is that? Right. Oh, brilliant. Thank you. Oh, wonderful. Okay, so you've got a general base there, removing the proton from the 2' hydroxyl nucleophile, making it an orders of magnitude better nucleophile. And you want a general acid to protonate the oxyanion leaving group, greatly for assisting that. And if we look at how it happens when we look at the crystal structure, then this guanine nuclear base is acting as the general base, and this adenine here is acting as the general acid. In addition to that, there's two other components, I should say. You have alignment for the inline trajectory of the nucleophilic attack, and the G is also stabilizing the phosphorane transition state. But when proteins do these kind of reactions, they can bring to bear 20 different amino acid side chains covering quite a wide range of H chemistry. By contrast, what have we got in RNA? Not that much. We've got 4 rather similar nuclear bases, and you saw a moment ago how those could be employed. We've got a 2' hydroxyl group, and then we've got a charged phosphodiester linkage, which binds hydrated metal ions, and they can be brought to bear as well. And if we look at the range, so we've done a lot of work over many years solving crystal structures of these ribozymes, probing the chemical mechanisms and so on. We understand some better than others, but I've listed here for these 8 ribozymes here, the general base and the general acid. Now you can see that nuclear bases are very widely used, particularly guanine as the general base in the cleavage reaction. And quite a number of these use adenine or cytosine as the general acid. But in addition, you see that the hammerhead uses a 2' hydroxyl as the general acid, and Pistol and the HDV and TS group use hydrated magnesium ion as the general base. So RNA actually is incredibly adventurous. It uses everything at its disposal. But that's all phosphoryl transfer. And really the question I want to ask is, how much further can we go? Well, at the present time, we don't know of a lot of natural ribozymes that are doing other chemistries. And for the most part, all we can do is to use test tube evolution. So use selection methods in vitro to create an RNA that will catalyze a different reaction. And one such I want to talk about now is a methyltransferase ribosome. So this makes a carbon-nitrogen bond, and I want to go into this and see how sophisticated a ribosome is this RNA. Can it do more sophisticated chemistry? So this is a collaboration with my former postdoc, Huang Lin, who is at Zhongshan Dashi in Guangzhou. And the ribosome that we've studied is this one here, which was isolated. So this was selected, just as I just said, it's a in vitro selected ribosome by Claudia Hurbartner's lab in Germany. And it's called MTR1. And what this does is it binds an exogenous O6-methylguanine, and it catalyzes the transfer of the proton from the O6, the methyl group from the O6 to this target adenine here. So the RNA is doing this reaction. So there's the O6 methyl. It transfers that to the N1 of the target adenine. That's this adenine here. Transfers to that position to make an N1 methyl adenine. And of course, it leaves exogenous guanine bound to the RNA. And because this is positively charged, it retards its mobility in polyacrylamide. So you can actually, this is the substrate strand effectively radio labeled. You can see that when you modify that, it's slightly retarded in the gel. There you can see the reaction is producing. That's the substrate, that's the product, and you can therefore follow the progress of the reaction and measure the kinetics by this means. Okay, so we decided to crystallize this and in fact solve the structure at 2.3 angstroms resolution. Turns out what is in the crystal is not the substrate, but rather the product. So the reaction has gone to completion. So we have N1 methyladenine in the RNA, and we have exogenous guanine bound. Okay, now what is the structure? Now, bearing in mind that the seed sequence here has got 1, 2, 3 helices, it's a kind of three-way junction. It's not very surprising that the product structure is a three-way junction. So you have these 3 helices, first one, second one, third one, and these two are approximately coaxial. Okay, now, equally unsurprising to me at least, was that all the activity goes on in the center. That's where the action happens. So if we zoom in on that, what we'll find is there are 4 planes of base interactions. And they're shown here 1, 2, 3, 4. The first 2 are simply cis-Watson-Crick pairs, normal Watson-Crick pairs. The top one are 3 adenines in a plane, so it's a triple, fairly weak-looking affair because there's a single hydrogen bond between each of these. And then in the middle is the real center of action in this ribosome. So the cyan shows the guanine, the exogenous guanine. The pink here is the target adenine, and then this is held by cytosine here and a uracil there. So if we look at the map in more detail, you see there I've labeled that as 6-methyl-G, but we know actually that it's just guanine. And you can see that it's incredibly well held. 3 hydrogen bonds on its sugar edge to this uracil here. 3 hydrogen bonds on its Watson-Crick edge to this cytosine here. A single hydrogen bond to the N6, the target adenine, plus the fact that it's stacked top and bottom. So it's really well held on there. Now, if you plot out the FO minus FC map for this, you see there's unassigned electron density about 1.5 angstroms from the N1 here. And if instead we model that as N1 methyl adenine, you see the density actually fits perfect. And there's no sign of any density here corresponding to 0,6-methyl-1. So that's the evidence that we have a product, the reaction has gone to completion. Okay, now, of course, the question I'm trying to answer in this talk is how chemically flexible is RNA? Is it doing this with a recognizable, sophisticated chemical mechanism? I'm a chemist. I want to get under the hood of this and understand how it works. Okay, well, now the first 2 points about how it works are obvious. I would have guessed the following, but let's go through them anyway. The first thing is, of course, this guanine, or 0,6-methyl-guanine as it starts out, is incredibly well bound into that site. So, effectively, the entropy of binding this is offset because you've already done that in the ground state. Put another way, you've greatly increased the local concentration of the reactor. So all of that you could have guessed. Second thing, the reaction. So it's an SN2 reaction. We have sp2 molecular orbital on the nitrogen, the lone pair here, is going to donate. You can overlap the wave function with a sigma star orbital of the CO bond here. And to do that, this, of course, has trigonal symmetry, sp2, and so that angle would be 120 degrees. What we measure in our crystal structure is 118 degrees. So it's almost perfectly aligned. So you've got the 2 advantages thus far. You've got the high local concentration, paid for the entropy of binding, and you've got an alignment. But there's more. There's quite a lot to this. Okay, so we then did mutation analysis. Clearly, the 6-methyl-guanine substrate is going to be held by the U and by the C. They're likely to be important. So let's do some mutagenics. Is that 5 minutes before the 20? Right? I've been talking for about 15, so okay. Yes, so we changed the U to a C, and in a separate experiment, we changed the C to a U. When we change the U to a C, this is, you can see, you can observe product here. The reaction, we can observe a progress curve. It's going at about 1/30th the rate of the selected sequence without modification. However, When we change the C to a U, there's no sign whatsoever of our product. We can actually do this reaction for 5 or 6 days. There's no sign of the product. This ribosome is dead. That implies there's a very important role for that C. Okay. Now, what could that C be doing? Well, in the ground state of the C, it's of course unprotonated, and there is no proton here. Similarly, there's no proton here because this is you've got the methyl here, single bond, double bond, therefore there's no iminoproton on there. So there's no hydrogen bond. But when we remove the methyl, when we restore that double bond, restore the single bond, we need a proton on here. So we would need a general acid in the course of that reaction to protonate that nitrogen. Having put this cytosine here, potentially you've got the general acid. Now the pKa of isolated C in free solution is about 4.5, 4.3. In this environment, I would expect it to be raised, probably by 1 or 2 units. And if you protonate this, then you get another hydrogen bond, and now you've got your general acid because this is just poised, ready to flip that proton over onto N1. So here is the proposed mechanism for this. We start out, let's say, I'll divide it into 2 steps that I don't believe are really separate. But let's say the first step is activation, where we're going to protonate that C10, and we've now got a proton on here. This is now ready to bind the exogenous O6-methyl guanine, and there we get the extra hydrogen bond by virtue of that. Now, this is ready to react now. So the nucleophile, the nitrogen N1 here, is ready to attack that carbon, and it's a beautiful smooth passage of electrons, flip, 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 and in the process, we make a new carbon-nitrogen bond, we break that bond, and the proton flips, restoring neutral cytosine as an iminoproton on the nitrogen. And in the process, rather like in a semiconductor, a positive hole moving in the opposite direction, the positive charge is relocated from here onto the N1 methyl adenine. Now, if that reaction is as I've described here, it should be pH dependent because we require this protonation of the cytosine. So we very carefully measured the pH dependence of this reaction, and you can see it's kind of bell-shaped. But previously we were measuring rates down here. If we measure the rate up at 5.5, it's significantly faster, and this corresponds to a pKa of 6.1. Now I should say I sort of reverted to my roots of what I did my PhD on recently, and done some quantum mechanical calculations on this. We calculated the expected pK and we calculated 6.2. So I think it's in very good agreement. But then we did some experimental work. We did some atomic modification on this. So this is the cytosine there. Then, thanks to my good friend Joe Pitcher early in Chicago, who had synthesized various C nucleoside analogs, this N1C form has a pKa that's raised up to 11.4, and yet that modification doesn't actually physically change the interface that's making the contact. That's down unmeasurably slow. Then what we did, Joe had synthesized another compound, retaining that C nucleoside there. He made an ASA modification at this position, so he changed the carbon for a nitrogen, and that brings its pH right down again to 3.7, and that restores the activity. So we did first mutation, killed the activity. The second mutation, in the context of the first, and it brings it back again. I find that pretty powerful evidence, and so this really is a very sophisticated ribosome. It's doing general acid catalysis. It's doing just what these natural ribosomes, like twister ribosome and so on, are doing. It's using nuclear-based mediated general acid catalysis. I find that impressive, given that it's only the product of 11 rounds of selection. Well, I should say this has become a very hot area. Actually, we published this in Nature Chemical Biology a few weeks ago, and back to back, there was a paper from Claudia Herbartner, also with the structure of the same ribosome, and deduced essentially the same mechanism. My former postdoc, Alistair Murchie, who's in Fudan in Shanghai, he's recently isolated and then solved the structure of a completely different methyltransferase that uses the natural methyl donor, SAM, S-adenosylmethionine. And my friend Joe Picciarelli has recently published also a self-alkylating ribosome. So how am I doing for time? Yeah. Okay, look, give me a couple more minutes and then I shall stop. So I just wanted to make a general point. I'm not going to bang on about this point because at the last meeting, which was online, I talked about the final little aspect. But I think what I've just shown you shows very well that RNA is certainly not just limited to phosphoryl transfer. It can do a very good job on methyl transfer, but still an RNA world would have required so much more. How can we do that? Well, actually, you know, proteins can't do everything either. Proteins can't do redox. There's lots of things proteins can't. How do they do it? They use coenzymes. So why not RNA doing the same thing? Not only that, quite a number of coenzymes look like they came out of the RNA world. They got bits of adenine on them and so on. And could they bind to RNA? And could they use these to widen their chemical space? Well, it's a good precedent for that because RNA certainly binds coenzymes. There are lots of coenzyme binding riboswitches that bind, for example, there are lots that bind SAM. TPP, extremely powerful coenzyme. That's the widest group of riboswitches. FMN, cobalamin, there's a whole load of things. I'll just show you one example and then I'll stop. But the widest group are the TPP. And what I've done here is to show the distribution of these. I mean, I'm not a phylogeneticist, but I can look at these things and clearly see that TPP riboswitches are extremely widely distributed. And therefore, plausibly, I think most people think these go back to Luca. So they could well have come out of the RNA world. And if we look at the structure of the TPP riboswitch, now the key part of TPP is this thiazole ring. That's where you're going to do the chemistry. You're going to generate a carbanion here, and that's a very powerfully reacting center. And if we look, there's the structure, and effectively it's straddling two helices coming down here and down here. And the thiazole ring is clearly displayed there. And one could imagine, and this is what we want to try and do, doing some selection on this to modify the nucleotides around here to create a binding pocket for example, alpha keto acids. So we'd like to look, can we make this into a ribosome that'll decarboxylate pyruvate? Okay, so that's it, except to say then, what have I just told you? I think RNA has fantastic potential. I think there is all the proof of principle we need that RNA could catalyze an RNA-based metabolism. We know that it carries out phosphoryl transfer reactions. Lots and lots of data we have on that. We've now shown that it's pretty good at doing carbon nitrogen as well. And of course, there's a precedent for that naturally, because arguably the most important reaction the cell does, which is making condensing amino acids to form polypeptides, peptidyl transferase, is a ribosome. And then lastly, going beyond that, well, I think that coenzymes are the way to expand the chemical space of RNA. So that's where I'm going to stop. I hope I haven't gone on too long. So I want to thank the people that are involved in this. Tim Wilson has been in my lab for, gosh, a long time, 30 years, I think, practically. And every day, Tim and I go out to have coffee in the morning and talk about RNA catalysis. It's a passion of ours we've held for many years. And then this has been a fabulous collaboration with my former postdoc, Huang Lin, and his student, Deng Jie, and they're in Guangzhou at Sun Yat-sen Dashi. Okay, so thank you for your attention. Thank you.